Now, we are still talking about differentiation. Actually, also the next chapter in our textbook, chapter 4, will be about differentiation, applications of differentiation. Now we are still in chapter 3, where there are 2 sections left. Now, the first subsection, which I'm going to talk about today, is section 3.11 in our textbook, which is called linear approximation. And differentials. Actually, this section already explains an application, important application of the theory of differentiation. But at this stage, it's a little bit too early to discuss this in more details. So in this section, this will be just explained very roughly. And we will, next semester, we will talk more about similar topics. Now, what was the reason why we considered derivatives? So we defined the derivative as a special limit and we gave it two interpretations. One of them was as a slope of the tangent. I explained already why we are interested in the tangent. The main reason is because the tangent line, a line is the most simplest function you can think about. And the main reason why we are interested in the tangent is because we want to approximate a maybe complicated function by something which is simple. So in some applications, we do not know, we do not have a lot of information about the function. For instance, we do not have an expression which just knows certain values by doing some measurements, some experiments. And sometimes, for instance, from a function, you know the first derivative at some point and the function value. But this is already enough to approximate the function for values x which are close to this value a, where you know the function value and the derivative. Okay, so if we know the function value at some point a and we know the derivative, then we know that we can approximate the function around, if x is close to a, by the tangent line. Okay, and this is called the linear approximation. Or also sometimes called tangent line approximation. And this function here, if we call it L of x, we also call this the linearization at x is equal to a. Okay, so you can think about the function f is very complicated. Maybe you do not even have an expression for the function, but you know from somewhere you know the value of f at a specific a, because maybe it's easier to evaluate or it's easier to measure at a, and you know the derivative at a. And if you have this information, you can already get an approximation for f of x where x is close to a. Now, this is something, I shouldn't waste so much space. So this is something you have seen already in physics, I guess, quite a lot. For instance, if you look at a very easy function, the sine of x, the point you're interested in is equal to 0. Okay, then, of course, you know that the tangent at 0 is just the line x. So you can approximate for x close to a, close to 0, you can use x in order to approximate sine of x, which is more complicated. You have seen this in physics like several times, I suppose. Now, if you consider another point, a is equal to, let's say, pi over 4, of course, you get a similar approximation. So here the sine of x. Okay, so we have the cosine at pi over 4, which is 1/2 square root of 2x minus pi over 4 plus 1/2 square root of 2. And this would be another approximation of sine of x, okay? But of course, there is a difference here. This approximation is good if x is close to 0, and this approximation here is good only if x is close to pi over 4. So for instance, if you have a value of 0.1, okay, then you can roughly approximate sine of 0.1, just 0.1. Now, for such a simple function, okay, you have seen in physics sometimes if you want to prove some result and it's not possible to solve the original equation or the original expression you get, then sometimes you replace sine of x by x, and then it's possible to solve the resulting equation. A famous example from physics is computing the period of a pendulum. Okay, so you have maybe seen this. Now, of course, if you have more complicated function, this seems to make more sense. So if you have this function here at x is equal to 1, okay, so also here you can easily get the tangent line approximation. Okay, so for this you have to compute the derivative. So the derivative of this function is equal to ln x plus 1. So you see that the derivative at 1 is equal to 1. Okay, so the tangent line approximation becomes x minus 1. Okay, or if you have an even more complicated function like f of x is equal to, let's say, 1 plus the cosine of x to the x. Okay, now and let's look at the point x is equal to 0. So a is equal to 0. Okay, now we have seen last time how to compute the derivative. So you have to you write the original function. Sorry. So a is equal to 0. So you write the original function as e to the x ln 1 plus cosine of x. Now you can compute the derivative. Okay, so you have to use the chain rule because this is a composite function. The derivative of the outer function is the function itself. Now the derivative of the inner function, which is ln 1 plus cosine of x plus x over 1 plus cosine of x. Actually, here you have a minus sine of x. Okay, so you see that the derivative of f at 0. Okay, so this guy is 0. This guy is the ln of 2. This guy is 1, so you have ln of 2. Okay, so you can approximate this complicated function. I delete this here. So you can approximate this complicated function by ln of 2x plus the function value, which is 1. Okay, and this might be easier to, you might object, maybe we do not know ln of 2. Okay, but you can get first an approximation for this, and then for x close to 0, you can use this expression in order to approximate this function. Now, this is the basic idea, and if you look at the example in our textbook, okay, there is also an example where they discuss for a certain function, okay, for which range of x is the approximation good. I think this is one of the examples in your textbook. For the function square root of x plus 3, first the linear approximation at a is equal to 1 is computed, and then the range of x is found for which the error between the original function and the approximation is small, and the method which is used in the textbook is Maple. So because if you want to understand the error here, okay, it's not so easy. So one way is you plot those two functions, okay, and you try to find the range for x where the difference is small, okay. But I don't want to go into details of this example because I think it doesn't show a lot. Because what we want to do is we want to approximate this function by this one, okay. So normally you do not know this function, okay. That's why you want to approximate. If you know the function anyway, then you do not have to approximate it. So, but you see from here there is an important issue which we are not able to address at the moment, namely how to estimate the error. And this is important. If you do approximation, but you are not able to approximate the errors, the result which you get is useless. Okay. So, for instance, if x is equal to 0.1, this will tell you, okay, that the sign of 0.1 is about 0.1. Okay. Now, we are able to compute the sign because the sign is on the calculator. But if we are not able to compute the function, okay, of course the most important question is how good is this approximation? Okay, if you cannot say anything about how good the approximation is, it's useless to approximate it. Okay, so here is the important question. The main question actually is, okay, are we able, or can we estimate the error, okay, the difference, okay, for a certain x? And this is something we are not able to do at the moment, but we will do this next semester. So we will look into this approximation problem in much more details next semester. Because actually, this is an important issue because this gives you a way actually to compute the sign, okay? Now, the reason why we think we understand the sign is because the sign is on the calculator, so the calculator knows how to compute the sign. But actually, we have never discussed, okay, how does the calculator do it? Okay, how does the calculator compute the sign? Now, this already gives you a rough idea how the calculator does it. Namely, the calculator replaces the sign by something which is more easier. Okay, and if you tell the calculator, okay, compute the sign of 0.1, he will evaluate something which is easier instead of it. But this approximation is, of course, not good enough. So we will learn how to approximate sign and also more complicated functions more precisely next semester. And this will be an important issue next semester. OK, so as for now, the only thing which is important is that if we know the function at some point, we know the function value at some point, we know the derivative at some point, we can approximate the original function around this point by the tangent line, okay? And actually, differentiation, the theory of differentiation was developed because of this question here, okay? So because of the question, if you have a complicated function f, you might be able, for instance, you might have an expression. For instance, this expression, you see, it's easy to evaluate at 0, but it's not so easy to evaluate if you have 0.0001, okay? And this gives you an easy way, okay, to be still able, without calculator, to find the values of this function for x is close to 0. This was one of the reasons why differentiation, the theory of differentiation, was developed. Okay, so this is the first main thing in this section on linear approximations and differentials. The other main thing is to define the so-called differential, which is actually just notation which will make it more convenient to talk about this stuff here. Okay, so now, what we want to do is we want to give this symbol here, dx and dy, meaning, okay? But the way we are going to define these quantities, okay, is just to make it easier to talk about such issue, okay? It's not really related. This will not be really related to dy over dx. So we will define those two quantities, okay? But the difference of those two quantities will not have the meaning of dy over dx. Okay, now this is something you might have seen in physics already quite a lot, that they talk here about, so they talk about these two quantities, okay? Up to now, we only consider the whole symbol dy over dx. Now, what is dx? So dx, we look at it as an independent variable. Okay, and dy, we look at it as a dependent variable. So actually, dy is a function of dx. Okay, and how is this function defined? By this expression, dy is equal to okay, so dy is this function here. Dx is the variable, and for a certain dx, you compute like this, dy. Okay. Now, this definition obviously makes sense, okay, because it's kind of, we wanna divide it by dx, okay, and then we have that dy over dx is the derivative, okay. That's the motivation why we define the symbol like this here. So, what is the meaning? So those two dx, dy are called differentials. What is the meaning of them? Okay, so let's plot a graph. Okay, so maybe like this here. So y is equal to f of x, and let's consider the tangent at some point. So let's say this is the point A. Okay, now if we change x from a to a plus delta x, okay, so this is what is delta x here. Then we know that this here, delta y is the change. This length here gives us the change in the function value, and what we see here, this here, okay, is the change if we replace the function by the tangent. So if our independent variable is equal to delta x, this here will be delta y. Okay. So the meaning of delta y, if our delta x is equal to dx, the meaning of delta y is okay, the change in the function value if you replace the original function by the tangent. Okay, so you have that dy is roughly delta y. This is not very mysterious. Okay, this is you should have recognized by now that what I write here is exactly the tangent line approximation. Okay, because this delta y is equal to f of x plus, or f of a plus dx minus f of a. So you see that you can write this as f of a plus delta x is roughly f of a plus dy. And if you plug for dy, for dy you plug in this here, you see this, what I write here is, it's just another notation for the tangent line approximation. Okay, so the reason why we consider this notation here is just to be able to talk more conveniently about what I have talked before. Okay, so this is just notation. There's nothing else behind this. Okay, so maybe let's look at one of the examples we have discussed previously, just to see how this fits in. Okay, so for instance, for the function f of x, okay, so you see that the derivative okay, so you can write this now. Using our notation, you can write this as dy is equal to ln x plus 1 dx. Okay, and our tangent line approximation at a is equal to 0 becomes f of dx is roughly, So if you just use the same here, f of 0, sorry, a is equal to 1. So here you have, 1 plus 0, 1 plus dx is roughly, so f of a, which is equal to 0 times this here. And this here evaluated at 1, so you have dx. The same as we have, the same as we had before. Okay. Now, so this kind of notation, this is just notation, okay, just to write what we have done previously in a different way. Now, this notation is frequently used. You have an example in our textbook, so it's frequently used if you measure something and it involves a measure error, and you are interested in, okay, so you know that you have a relationship between two quantities. You measure x, which involves an error, some delta x, and you are interested, okay, what is the effect, the impact of this error on the resulting quantity. And in this situation, okay, we very often replace the original function by the tangent line approximation and use the tangent line approximation to get the resulting, to approximate or to estimate the resulting error. So maybe you shouldn't be confused here by this, okay? I just introduced notation, okay, to write this differently, but it's actually exactly the same as what I have done at the beginning. Now, okay, so let's look at this example which we have in our textbook. So here we have measured the radius of a sphere as 21 centimeter, and then we have some error plus minus 0.005 centimeter. Okay, and the question is, what is the maximal error when computing V. Okay, so these are the typical questions. So we are interested, we have some quantity. We have some relationship between two quantities. We measure one of them, and we have some error, and we are interested, okay, what is the impact of this error here, okay, on the quantity V. Now, you know that V is equal to 4/3 times pi times r to the cube. Okay, it is easier here to replace the function by the tangent line approximation. Of course, you could, because this expression is quite easy, you can easily also analyze the original function, but this is just an easy example because sometimes this relationship is much more complicated. Okay, so you see that the derivative with respect to r is 4 times pi times r square. Or in our notation, we can write this as dv is equal to 4 times pi times r square dr. Okay, now our dr here is roughly this here. So our error, you can approximate it by dv. Okay, but dv is 4 times pi times r square times dr, and you can bound the error. If you replace the original one by this one, you can bound it by 4 times pi times r square times the bound of dr, which is 0.005. And you plug everything in and compute it. Actually, in the textbook, you have 0.05. So you plug everything in, and then you get here 277 cubic centimeter. Okay, so that's the effect of this uncertainty for the radius, okay, on the volume of the sphere. Okay, so you see from here, okay, that actually the reason why we introduced the differential is because it gives us a more convenient way to write things. Okay, and in such questions, this notation is frequently applied. Okay, so any questions to this? Okay, so in this section, two main things I explained. The first thing is that we can use the tangent in order to approximate the original function. Of course, we know this already from the time where we started to motivate the theory of differentiation. And we saw that the important issue later on will be to find bounds for the error. Okay, this is something we will do next semester. And the definition of differential, which is just notation. You also find in our textbook some application to physics. As I have explained, for instance, this simple approximation here. And also for the cosine, this would be the tangent line approximation. Okay, such simple approximations you have used already in physics. One of the classical questions is to compute the period of a pendulum. You have a pendulum, and you want to compute the periods. Normally, what you get is an equation which you are not able to solve unless you do something like this, some approximation like this here. Another application is in optics, where if you consider light rays which have a shallow angle, then you normally use this approximation here, which leads to the so-called Gaussian optics. So maybe you have heard this in physics. I don't want to talk about this in more details because I'm not good in physics. Actually, I dropped the course when I was a freshman, so I don't know a lot about physics. Maybe you have discovered now already that in physics, courses on physics, you need now already quite a lot of mathematics you have actually not learned yet, and we try to catch up. This was the reason why I dropped the course when I was a freshman, because I don't like to see a lot of mathematics which I do not understand. So, but this is the problem in learning physics, so you will need lots of things which you will learn much later in this course here. But it makes still sense. I hope you have discovered this by now, that to look at things more precisely and to look at simple things, or things which look simple, like limits and so on, from a different, more precise angle. This is normally what physicists don't do. Okay, so the final section in Chapter 3 is Section 3.7, which is about higher derivatives. So we haven't talked about this yet. Of course, this is an obvious concept because the derivative of a function itself is a function. So you can compute, you can try to find its derivative, which will naturally lead you to the second derivative. Okay, so its derivative. Actually, we should write this like this here, but we have several notations for this. So this is the standard notation, or if we use Leibniz notation, then we will write this normally like this here. Sometimes we also use this notation, where D is so-called differential operator. You will see this more in physics. This is also, every time this is emphasized in our textbook, but this is not used anymore later on. But you will see this notation maybe in some applications. So the main question, of course, here is, okay, why are we interested in the derivative of the derivative? It obviously tells us something about the first derivative, okay, because we can interpret this as the tangent of the first derivative. But you know also from physics that it makes sense to talk about, so actually this is a rate of change, okay, and it makes sense. You know this already, you have discovered this already in high school, that it makes sense to talk about rate of changes. For instance, if you have the position function, then the first derivative is the velocity, the second derivative will be the acceleration. And the second derivative is actually the rate of change of the original rate of change of the rate of change of the function. Okay. Maybe let's look at some examples. You find in our textbook some nice examples. Let's maybe consider one of them. If I find it. Take a look at the examples in this section about higher derivatives, section 3.7, example 1 in your textbook. This is a quite nice example. Look at the problems. This is page 240. Page 240, example 1. This is a quite nice example to get a feeling for derivatives. So you have given three functions. The question is, okay, which one is the original function? Which one is its derivative? Which one is its second derivative? Okay, so page 240. So who knows the answer? For this ordering. So here the correct order is APC. Now, how about example 3? If you know it, then shout it out. CBA, right? You see, it still involves. You have to think a little bit about it. So it's not too complicated, but at least this will help you to develop a good feeling for derivatives. Okay, so maybe let's compute some other second derivatives. So for instance, if you have a function given implicitly by this equation here, and you want to know the second derivative, okay, so actually here you can use again the method of implicit differentiation. One method, because this is an easy equation, you could solve first for y, and then you can just use our rules in order to find the derivatives. But actually you do not have to solve for y. So first we just take the derivative on both sides in order to get the first derivative. So we have 3x squared plus 3y squared times the derivative of y is equal to 0. So from here you see that the derivative of y is equal to minus x squared over y squared. And now in order to find the second derivative, we just take here the derivative. Okay, but remember that y is a function of x. So what you get by the quotient rule is y to the fourth. Okay, then you have 2x y squared minus x squared 2y times the derivative of y. Okay, now you plug in what you know already. You know this expression for the derivative of y in order to, sorry, this should be 4. This looks like. Okay. Now you plug this in here. So what you get is minus 2x y squared plus x to the 4. So you have a 2 here, x to the 4, and one y cancels, so over y to the y over 4. Now you multiply everything by y. Okay, so you get y to the fifth, and here you have 2x y to the cube plus 2x to the 4. So we take out minus 2x, and what remains here is y to the cube plus x to the cube over y to the fifth. But this here is, if you look at the original equation, is 1. So the resulting expression becomes quite easy, minus 2x over y to the 5. Okay, so of course another method to solve something like this is first you solve for y, and then you take the derivative of the resulting expression. But as we have seen already previously, if you write this as the third root of 1 minus x to the cube, of course the first derivative is easy to obtain, but for the second derivative you would get a much more complicated expression than this one here. Okay, but which essentially then reduces to this expression. So you can try it on your own first to solve it for y and to compute the second derivative, and you will see that this using implicit differentiation is actually much quicker in this situation. Now, any questions to this? Another example are so-called differential equations, which are important in physics. So a differential equation normally is just an equation which involves derivatives of the derivative of an unknown function. So for instance, an easy example for a differential equation would be the second derivative of y minus 2 times the first derivative of y. Oh, let's see, right. Let's write here. Plus 2y is equal to 0. Okay. Now, in physics, such equations are very important. It's a so-called differential equation of second order, and your aim is to find the function y. So actually, your aim is to find all functions y which satisfy such an equation. Now, if you have an equation like this here, where all the coefficients are constants, okay, it's easy to guess a solution. Who can guess a solution here? Actually, you do not have to completely guess it, but you might have to guess that the solution should look like this here. Okay, why? Because we know that this function does not change. It does not change if we take the derivatives. The only thing which changes is the coefficient. Okay, but if we differentiate it twice, okay, it will appear everywhere, so we can cancel it. So the resulting equation might become much more easy. Okay, so you see that if you plug this in here, you have alpha square e to the alpha x minus alpha e to the alpha x plus 2 e to the alpha x is equal to 0. But e to the alpha x is always larger than 0, so we can cancel it. And we get alpha square minus alpha plus 2, which is alpha minus 2 times alpha plus 1 is equal to 0. Okay, so we get here two solutions. Alpha is equal to 2, and alpha is equal to minus 1. So we have found two functions, namely e to the. We have found two solutions, namely e to the 2x and e to the minus x, which both solve this differential equation. Okay. Of course, also the sum of those two will solve the differential equation. Actually, if you multiply this with a constant and this with a constant and sum them, you will also get a solution of this differential equation. So from here you see that a more general solution would be given by some constant e to the 2x plus d e to the minus x. Okay, all those functions here solve this differential equation, and you will learn in another class that these are all solutions. There are no others. Okay, so you see that we are not going to discuss in this course, okay, how to solve such more complicated differential equation. Is an important issue, and you will learn it in your own class on differential equations. Okay, so any questions to this? Now, as I have already explained, actually second derivatives have meaning in physics, like if S gives the position of a particle at time t, then we already defined the derivative as the velocity, and the derivative of the derivative is something which you have considered already in high school. This is called the acceleration. Now, of course, it also makes sense to look at higher derivatives. Okay, so you again consider the derivative of the derivative. Okay, of course, in physics, you have to ask the question whether the derivative of a has a meaning, so the rate of change of the acceleration. Also, this quantity is considered in physics, normally called j, which is the derivative of the acceleration. Okay, and this is called the jerk. Okay, and the meaning of jerk is if you have a fast change in the acceleration. Okay, you will feel this if you are sitting in a car, because it's it will cause a abrupt movement. Okay, and this is a quantity which is also important in physics. So this is now the third derivative. So you see from here already that it makes sense to look to consider higher derivatives. So in general, we define the nth derivative as the derivative of the n minus first derivative. Okay, so this is called the nth derivative. If you are sitting in a car, okay, and you cannot see the environment, normally the only thing you can feel are those two. Okay, you cannot feel the velocity, you cannot feel the displacement, but you can feel the acceleration and you can feel the jerk. Now, maybe let's look at some examples. So we will later on discover why it makes sense, okay, to look at the nth derivative. So of course the question arises, if you have a given function, why are you interested in the 1,000th derivative of this function? Okay, but we will later on discover that it makes sense to look at derivatives of arbitrary high order. Now, so maybe let's look at an easy example, x to the 5 plus 3x squared plus 2x plus 1. So for such a function, you can easily compute the derivatives. Okay, so the first derivative, 5x to the 4 plus 6x plus 2. Second derivative, 20x to the cube plus 6. The third derivative, 60x squared. The fourth derivative, 120x. The fifth derivative, 120. And the sixth derivative, 0. Okay, so you see for a polynomial, of course, if the order of the derivative exceeds the degree of the polynomial, which is here 5, then the derivatives will all be equal to 0. Now, okay, this is an easy example. Let's look at another example. There's another easy example. Would be this one. F of x is equal to 1 over x. Okay, so what is the nth derivative? In our textbook, you can find such examples. For more complicated functions, you are asked to find an expression for the nth derivative. Sometimes it's more complicated. This here is an easy case, easy example. So you see the first derivative is minus 1 over x squared. You see the second derivative is 2 over x to the cube. The third derivative is minus 3 times 2 over x to the 4th. So from here you can already guess, okay, what is the rule for the nth derivative. So you see that the nth derivative is equal to minus 1 to the n factorial over x to the n plus 1. Okay, so I guess you have learned this symbol in high school. Just maybe if you haven't heard it in English, this is called n factorial. And for instance, you know that the binomial coefficients is equal to n factorial over k factorial n minus k factorial. Okay, so that's what you have learned in high school. Okay, now, maybe you haven't seen, in mathematics we also sometimes use this symbol here, 2 factorial. Okay, what is the meaning of it? You can easily guess it. Here the step size is 1. Here the step size would be 2. Okay, so you have n times n minus 2 times n minus 4, and so on. Till you arrive either at 2 or at 1, depending on whether n is even or odd. So maybe you have seen this already somewhere else. So we also use this symbol, and in some applications, this is a suitable notation. Let's look at the final example. So an example which is similar. Okay, so for instance, we are interested in finding a formula for the nth derivative of a product. Okay, so you have a product of 2 functions, and you want to find an expression, okay, for the nth derivative. Okay, so this will be a generalization of the product rule. Now you start by with the case n is equal to 1, which is just the ordinary product rule. Now let's look at the case where n is equal to 2. So we have to take the derivative here once more. So we see this is the second derivative of f times g of x. Then we have the first derivative of f times the first derivative of g, but the same will appear here. So we have it twice, plus twice, the first derivative of x times the first derivative of g, plus, and then here the function f of x times the second derivative of g of x. Okay, if you try n is equal to 3, you will get easily a guess, which is this is the sum k from 0 to n choose k. The k's derivative of f of x times the n minus k's derivative of g of x. Okay, so similar to the kind of similar to the polynomial theorem, to the binomial theorem. Now, how to prove this? Okay, so something like this, as maybe most of you know from high school, is proved by induction. Okay, so we saw here already the case n is equal to 1. Okay, now assume this holds for all derivatives of order k smaller or equal than n. We want to prove it for n plus 1. So we have the step from n to n plus 1. Okay, so we want to find the derivative of the product of n plus first order. Okay, so we just take this is by definition is the derivative of this function here. Okay, so we can use here the induction hypothesis. So we have to compute the derivative 0 to n choose k. F of so we have here k. So we maybe I erase this just to have more space. Okay, so we have to take the derivative now, the first derivative of the term which was here in the sum, which is the k plus first derivative of f of x, and g is still the m minus k's derivative at x, plus the k's derivative of f at x times the n minus k plus first derivative of g at x. Okay, so you see that we take out the term where k is equal to n, which is equal to the n plus first derivative of x times g of x. So this is the term here, k is equal to n in this sum. And in this sum, we take out the term where k is equal to 0. Okay. In this case, the binomial coefficient is also equal to 1. So we have plus f of x and the n plus first derivative of g of x. So we still have the sum k from 0 to n minus 1, n choose k, f k plus 1 of x, g of n minus k of x, plus the sum k from 1 to n, n choose k. Okay, I drop now the x, so fk g of n minus k plus 1. Okay, now we shift here the index. So we have, this is f n plus 1 g plus f g n plus 1 plus. So the sum should go from 1 to n. Actually, it doesn't matter. So maybe let's shift the index here in the second sum, but it doesn't matter. Okay, so n choose k, f k plus 1, g n minus k plus. So let's shift here the index. So the sum k from 0 to n. So we have to replace k by k plus 1, 0 to n minus 1. F of k plus 1, g n minus k. Okay, now we can merge those two sums. Okay, so I will continue here. So we have f n plus 1, g plus f g n plus 1 plus. So you see this term is the same here for both. And you know that n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. Okay, so you have the sum k from 0 to n minus 1. N choose k plus 1. F of, so the k plus first derivative of f. And this we write here now as, sorry, here's n plus 1. We write this as n plus 1 minus k plus 1. Okay, now we shift the index again. So we replace k by k minus 1, and then the sum goes from 1 to n, and we take those two in, and we are finished. Okay, that's it. So such proofs, as you know from high school, are rather automatic. You do not have to think a lot. You just do it. Okay, so this is sometimes a quite helpful formula. Okay, so the nth derivative of a product is computed similarly, kind of similar. You can kind of similar as the binomial theorem. Okay, so you have the sum over k, n choose k, and then the k's derivative of f times the n minus k's derivative of g. Okay, so any questions to this? As I said, it's maybe at this stage it's too early to understand why we are interested in derivatives of arbitrary high order. Okay, so for instance, for a given function, why are we interested to know or are we really interested to know the 1000th derivative of this function? we will later on see, okay, that we are indeed interested. Okay, it's not just that we consider something which seems to be obvious. Okay, if we have the tool of differentiation, we just start from a function and keep on taking derivatives. This is not the reason why we consider derivatives. Okay, higher derivatives. Okay, so there is later on we will understand much more clearly why it makes sense to look at derivatives of arbitrarily high order. Okay, so any questions? Now, if not, then we go on to chapter 4. Chapter 4 discusses applications of the theory of differentiation. In particular, in chapter 4, we will already see why higher derivatives are helpful. We won't see why the 1,000th derivative of a function is helpful, but we will at least discover why the second derivative is helpful. The first topic we want to talk about is maximum and minimum values. Now, this is something you might have heard roughly in high school as well. So quite often we are interested in finding maximum, largest and smallest value of a given function. There are many applications, like if you want to produce a cane. Okay, normally you are interested in, okay, which shape should the cane have that the production cost is a minimum. So in many applications you are interested in minimizing something or maximizing something. Like you want to maximize if you're at a company, you want to maximize the profit. Okay, you want to minimize the working time and so on. So there is an obvious need, okay, in order for given functions to find maximum, to have a good machinery to find maximum and minimum values. Now, we first start by the definition. So we have to differ between two kinds of maximum and minimum values, so-called absolute and local. Okay, so first absolute. So C is called absolute maximum value, absolute maximum of f on D if f of x is smaller or equal than f of c for all x in D. Now, f of c. So you should differ here between maximum and maximum value. F of c is called the maximum value. Now, similar, you define minimum value and you find also in our textbook a definition of extreme values, which are extreme values which are maximum value and minimum value, maximum value or minimum value, and you have also extrema and extreme values. Okay, so you have, whenever I add value, I mean the function value. And if I do not add value, okay, I actually mean the point, C. Okay. Maxima, minima. So the plural of minimum is minima. And the plural of maximum is maxima. And the plural of extreme value, extreme is extrema. Okay. For some reason, our author is not using the these words here, but I checked whether they really exist, because they exist in German, and I'm using them already several years, and I was wondering whether they are really used in English. Seems to be also correct. Okay, so this is absolute maximum, and absolute minimum. And then you have a local maximum and local minimum. So you have to be careful here. You have a similar definition for local maximum value of f. You do not have to write on D if f of x is smaller or equal than f of c for x from a closed interval or open interval containing c. Okay, so here you need a closed interval. Okay, so this is something which sometimes causes confusion. For instance, if you look at the function, in our textbook, you have this function 3x to the 4 minus 16x to the cube plus 18x squared, where your domain is minus 1 to 4. Now I plot the graph. So the graph is roughly where those 2 points are included, because this here is minus 1 and this here is 4. Okay, so you see that, for instance, at 0, this function has a local minimum, which is not the absolute minimum, because the absolute minimum is here. Okay, you see that at minus 1, okay, the function has absolute maximum, and now the important thing: this absolute maximum is not a local maximum. Okay, because you cannot find the interval around minus 1, which is completely in the domain. Okay, such that this is satisfied here. Also, this here. This is nothing, okay. This is, of course, it's not. It is not the absolute maximum, but it's also not a global maximum, a local maximum, okay. Because once more, for a local maximum, what you need is an interval, okay, around the point, okay, which is completely contained in the domain, okay, such that this is satisfied here. So you have to be careful here, okay. This point here, because if I ask such a question in the midterm, okay, there are many students who always include this, okay, as a local maximum. This is not a local maximum. Okay, so but this is the definition of the textbook. We will see later on. This actually is essential for the method we will introduce in order to find local extrema. And this is essentially what we will do next time. So next time we will first try to find local extrema, and then we will also try to find a method in order to find absolute extrema. Absolute extrema sometimes are also called global extrema. Okay, any questions? If not, then we go on next time.